Okay, today we're talking about bonding, electronegativity, electron configuration, excuse me, and how it relates to bonding. Okay, so you need to know that a bond is a force, and it's the force that holds a group of atoms together and makes them function as a unit. In thermodynamics, we talked about bond energy. You know that you need to input, or energy must be absorbed in order to break bonds, and then when new bonds are formed, energy is released. Bond energy is defined as the amount of energy that's required to break a bond. Why do bonds want to form? Because when bonds form, they achieve a lower energy state. You need to remember that the universe is a lazy place, and the lower energy state anything can achieve, the more stable it becomes. Therefore, bonded atoms are more stable. An ionic bond is an electrostatic attraction. Electrostatic means it's a attraction based on charge between ions. Usually the reaction is between a metal and a nonmetal. And the hallmark of an ionic bond is one atom completely transfers its electrons to another. The cation, which is positive because it transfers its valence electron to the anion, which is negative. Recall that the only exchange of electrons that are happening are the valence electrons. The core electrons do not move. It is possible for you to quantitate the energy of an ionic bond by using Coulomb's law. If you've studied physics, you're aware of Coulomb's law. It is a law of charges. Since an ionic bond is an electrostatic charge, you can use Coulomb's law to figure it out. So there's the equation for you. The energy of the bond is equal to 2.31 times 10 to the negative 19th joule per Newton meter times Q1, Q2. That would be the charge of the ions over R, the radius between them. I'm going to skip over the practice problem and go to bond length. Okay. All right. Bond length is the distance where the repulsion of the electron and electrons of two different atoms and the proton of two different atoms is minimized. So here we have in the top picture to the left two hydrogen atoms that are sufficiently far apart that they have absolutely no interaction. As the atoms come closer to each other, they start to interact and they move closer. There's going to be some repulsion as the electrons become closer together. That repulsion will be overcome when the respective nuclei are happy to have the electrons within their attractive force. And remember, everything will be more stable when the valence electrons of each one of the hydrogen share and complete the 1s orbital. A covalent bond is a bond in which electrons are shared between two atoms. It results from the mutual attraction of the two nuclei for the electrons. A polar covalent bond is a bond in which one nucleus has a greater attraction for the electron than the other. This results in unequal sharing. Last unit, chapter 7, we talked about electronegativity and your favorite memory hook, that fluorine is a floozy. Electronegativity is defined as the ability of an atom in a molecule to attract shared electrons to itself. Last time I talked about this, I emphasized the ability of an atom in a molecule. These are two atoms unequally sharing their shared electrons. The way you find electronegativity is through the difference between the actual bond energy and the expected bond energy. They found out that some electrons were tugged to the nucleus more tightly. Fluorine is the most electronegative because it has the greatest effective nuclear charge for its size and is very, very attracted to electrons. The nucleus is like a tractor beam for any electrons within its purview, and it pulls them closer. Well, francium has the lowest electronegativity because it has a very big atomic radius and a very small effective nuclear charge. We talked about the trends of electronegativity in our last unit. You need to just remember them again. Okay, you can use electronegativity to determine the type of bond between two atoms. Here's how you do it. You have been given an electronegativity chart, and you find the difference between the electronegativities for the two atoms in a bond. I want to tell you now and over again, when you're determining bond type, you're talking about two atoms. Just two atoms together. Subtract the difference between their electronegativities, and if the result is greater than 1.67, the bond is considered ionic. Anything less than that, but greater than 0.5, is considered to be polar covalent, and anything that is less than 0.5 is considered to be nonpolar covalent. So here we have it in a nutshell again. Now, the difference between the Chem 1 and the Chem 2 explanation here is this is a continuum. If you shrinky-dinked yourself down and started asking two atoms how they were bonded together, none of them would say, well, I'm at the cutoff between nonpolar and polar covalent. It's a continuum of sorts. Okay. So for exercise 1, order the following bonds according to their polarity. Well, the difference in electronegativity between H and H is 0, so it is definitely nonpolar. I'm going to leave you to the rest because I do not have an electronegativity chart with me at the moment. All right, this gives rise to something called a dipole moment. And a dipole moment is based on the polarity of the bonds between two atoms. When a molecule has a charge distribution where there's a positive and a negative end, read that as being polar, the charge is dipolar and the molecule has a dipole moment. A dipole moment is fancy term for something that you already know. That means it's a polar bond. Since you were in 7th grade, you have been drawing water as a polar molecule with Mickey Mouse ears. That would be the hydrogen that has a slight positive charge, and Mickey Mouse's head as the oxygen molecule that has a slight negative charge. One could say, in Chem 2 terms, that it has a dipole moment. Okay, the way you would write the dipole moment, let's use hydrogen fluoride as an example. We know that fluorine is very, very attracted to electrons, therefore it has a negative charge, leaving the hydrogen with a slight positive charge. You write the dipole moment with this lowercase sigma. You have an arrow going towards the negative sign, and you put this plus thing near the plus side. So you would say that hydrogen fluoride has a dipole moment where the negative charge would be sigma minus and the positive charge would be sigma plus. Okay, remember that electron configuration is based on atoms attempting to form to get into a stable configuration. The stable configuration for any atom, the most stable configuration, is the noble gas arrangement. They are either going to transfer electrons or share them with other atoms. Two nonmetals will react to form a covalent bond. They share their valence electrons so that both of them are noble gas in character. Okay, I wish this would come apart. Here we go. All right. So, a nonmetal and a representative metal react to form a binary ionic compound, so that the valence electrons, with the valence electrons, so that they attain noble gas configuration. So if you had calcium, which has the electron configuration argon 4s2, and oxygen, which has the noble gas configuration helium 2s2 2p6, you can see that by ionically bonding, therefore transferring the valence electrons for the calcium, which are the 4s2, to the valence electrons of the oxygen, you can complete the noble gas configuration here. So you would have helium 2s2 2p4 now becoming argon. So it would complete this outer shell. Meanwhile, this would be the noble gas configuration, just argon. We talked about ionic radius a little while ago. You remember that cation is smaller than its neutral atom because it has lost an electron. There's a greater positive charge, a greater effective nuclear charge pulling on the remaining electrons. And an anion is larger than its neutral atom because the extra electrons have reduced the effective nuclear charge that those electrons feel, because there are more electrons now than there are protons. I spoke about isoelectric ions. Those are ions that have the same number of electrons. So O with a -2 charge, fluorine with a -1 charge, sodium with a +1 charge, magnesium with a +2 charge, and aluminum with a +3 charge are all isoelectric. They have the same number of electrons. They have different number of protons pulling in the electrons. The greater number of protons, the smaller the size. Therefore, of this list, aluminum +3 is the smallest. It has the most protons acting on the electrons. Now let's talk about lattice energy. Okay, lattice energy is the change that takes place when separated gaseous elements are packed together to form an ionic solid. It's also known as the energy released when an ionic solid forms from its ions. What you need to be able to do is converse about why two things would come together and form an ionic compound. All ionic compounds at standard state are solids. So somebody would be asking you, why is it that calcium and oxygen would like to come together and form an ionic compound? That's because they would be releasing energy when they came together. So this is a state function because the steps that lead to the formation of the ionic solid can be added together in any way. So if someone were to give you the lattice energies, you would add them up, and you could tell someone why they would be attracted to each other and form an ionic compound. Once again, you can calculate lattice energy using Coulomb's law because this is an electrostatic attraction. So lattice energy is equal to K, which is a constant, the charge of the different atoms and the radius. Okay. If you have a big charge, you're going to have a big lattice energy. If you have a big radius, that means if you have two large atoms, you are going to have a small lattice energy. So how you would use this, and the way generally somebody asks you a question, rarely, on the AP exam would be this. predict the lattice energy between magnesium chloride, magnesium oxide, and magnesium bromide. Okay, so to do this, you would see that the charge between magnesium chloride, magnesium is +2, chlorine is -1, magnesium oxide is +2, -2, and lithium bromide is +1, -1. So magnesium oxide would have the largest lattice energy because it has the biggest charge in the denominator of that equation, and it is not hugely, neither one of the ions are hugely large. On the other hand, magnesium chloride would be the second because it has a +2 charge and a -1 charge in the numerator, while it would have a relatively small ions in the denominator. Lithium bromide is going to have the least amount of lattice energy because each one of the charges are 1, and lithium is a large molecule, so the denominator of that equation would be kind of large. Okay, that takes care of those notes.